Now let's look at the popular algorithm for hard clustering called K-means and see if we can connect it to the general form of the expectation maximization. So it would be really cool to derive it as a special case of EM and to fit it into a general framework. So hard clustering, we have a data set of points and we want to assign each data point to some of the clusters. And now we can't say that some data point belongs to several clusters simultaneously. Now each data point should be assigned to just one cluster. Okay. So the K-means algorithm suggests you to solve this hard clustering problem in the following way. First of all, let's initialize the parameters randomly. And here the parameters are just means, so the locations of the cluster. We don't have weights pi, and we don't have some shapes of the clusters sigma, so just locations. And then in iterations, we're repeating two substeps until convergence. So the first substep is to for each data point, find the closest cluster and assign this data point to belong to this cluster. So each data point is assigned to belong to the closest cluster to it. And by closest, I mean according to Euclidean distance. And on the next substep, K-means suggests you to update the parameters by finding, so for example, to update the first Gaussian, the first cluster centroid, mu1, we'll have to find all the data points which were assigned to the first cluster on the first substep, and then find their average, which will be the center of this cluster, updated center. And then we repeat these two things until convergence. So if you look carefully at this algorithm, it looks really similar to the EM, right? We also have random initializations, and then we, in iterations, repeat two steps, which also look really close to the stuff we had in the EM. First of all, we compute some property for each data point, and then we update the parameters by using these properties. So let's see if we can somehow convert our Gaussian mixture model and EM applied to it to obtain exactly this K-means algorithm. So to prove that the K-means is just a special case of this EM algorithm applied to Gaussian mixture model, or maybe to some other model. So first of all, we have to say that we don't have these additional parameters, right? So let's say that the covariance matrices, so the shapes, are all identical matrices, which means that all the shapes of each Gaussian is just uniform circle with fixed radius, and the prior weights, pi, are all uniform also. So they equal to 1 divided by the number of clusters. This way we'll have only mu as the parameters of our Gaussian mixture model, or kind of restricted Gaussian mixture model. And then the density of each data point, given that we know the cluster, now looks like this. So it's some normalization times exponent of 0.5 times the Euclidean distance between x1 and mu c, where mu c is the center of the Gaussian number c. You can prove that this is exactly the formula for multidimensional Gaussian, or multivariate Gaussian, if you have identical covariance matrix sigma. So if it's equals to identical matrix. Now let's look at the E and M steps of this restricted Gaussian mixture model. On the E step, the expectation maximization algorithm suggests you to find the minimum of the chiral divergence between the variational distribution Q and the posterior distribution P of t given data and parameters. And if we're going to do it, we will find not hard assignments, but soft assignments, right? As we obtained in the Gaussian mixture model. So for each data point, this Q will say with which probability it belongs to one cluster or another, or one Gaussian or another. And this is not what we want. We want to derive K-means from this model. So we want this step to be hard clustering. How can we do it? Well, let's find not the best optimal Q, but Q among some family of simple Qs. So let's look at the Q among all delta functions, where delta function means that this probability distribution takes one value of probability 1 and all the other values with probability 0. So it's really certain about what the outcome will be. So let's imagine that the posterior distribution looks like this. So our data point belongs to the cluster number 2 with probability like 0.6 and cluster number 1 with probability 0.4. What do you think what the delta function approximation will be? So what will be the closest Q to it according to KL distance with among the family of delta functions? Well, it will be a distribution like this. It will put all the probability mass into the class that had the highest probability according to our posterior. So by restricting the set of possible Qs on the A step, we're actually approximating the actual posterior distribution with delta functions. And this way, the optimal Q on the A step will look like this, right? It's some delta function. So it's probability 1, then Ti equals to some predefined value, and 0 otherwise. And what is Ci? What is this predefined value? Well, it's the most probable configuration according to our posterior distribution. So we have to find Ci which maximizes the posterior probability of the latent variable Ti, given the data and the parameters theta. Recall that the posterior distribution itself is proportional to the full joint distribution, which is x given t times p of t, and parameters. And we also have some normalization constant, but we don't care about it because we want to maximize this thing with respect to Ti, or with respect to C, which like with respect to the value of Ti. So normalization doesn't change anything. And if you recall, this thing equals to normalization times the x given t, which is exponent of minus 0.5 times Euclidean distance, and times the prior. And we agreed that the prior will be just uniform, so it doesn't depend on C. And we also don't care about it when we maximize this thing. So finally, we want to maximize this expression with respect to the value of Ti. And we have normalization 1 divided by z, and we have pi of c, which both actually doesn't depend on c. So we can throw it away and it will not change anything. And maximizing the exponent of minus something is the same as minimizing this something. So we can just minimize 0.5 times Euclidean distance. And finally, we have an expression like this. So our optimal Q from the E step is the same as, is just a delta function, which takes the value of argminimum of the Euclidean distance, so the closest cluster center, with probability 1. And it has probability 0 to be anything else. Okay? So this is exactly like we have in k-means. So, which means that this restricted Gaussian mixture model, if you apply EM to it, and if you restrict your possible values of the variational distribution Q on the A step to be delta functions, you will get exactly the same first substep of each iteration. So now let's derive the formula for the M step on the blackboard and see how it's connected, how does the formula for the second substep of k-means connects to the M step of the expectation maximization applied to this restricted Gaussian mixture model with this particular choice of Q, which is a delta function.